Hi guys. So I know I left you with a cliffhanger last time. Who is Q? What is Q? So here we are back with chemical equilibrium, and we're going to find out what Q is, the reaction quotient Q. And basically, Q is calculated the same way as the equilibrium constant K, but it is not the constant at equilibrium. It is for at initial concentrations. Now, when we say initial, we don't necessarily mean at the beginning. We mean at this point in time. So if we're saying, okay, we know what the equilibrium constant K is, and here we are at these concentrations right now of our reactants and our products. How does that moment we're looking at our experiment or our reaction compare to what it will look like at equilibrium? Are we at equilibrium? Have we gone to too much product? Do we have too many reactants? We need to make more product. So Q is what we use to compare to K to know where we are at this moment in time. So let's take a look at that. So here we see, and I don't want you to memorize these. We really want to understand the trends here. So let's take a look at an example. Okay, so let's keep our example really simple. Okay, so let's keep our example pretty simple. We don't need to be elaborate here. And remember, I'm using my little pad and stylus, so not easy, so my handwriting is going to be a little wonky here. Okay, so let's use something like we're just going from A to B. Just a basic reactant to product here. And let's say that our concentrations right now at this moment in time, we've got A is 4 molar and B is 1 molar. Keeping these numbers simple just to make a point. And we're going to go with this reaction, the equilibrium constant equals 2. Let's go with that. Okay, so Q is calculated the same way that K is. So our Q is going to be product divided by reactant, right? So our Q right now is 0.25. So our Q is indeed smaller than K. Well, if our Q is smaller than K, then that means that there's not enough product. So K is at equilibrium. That means that our concentrations of reactants and products are going to stay constant, and our rate of the equation is going to stay constant and be equal for forward and reverse reaction. So if Q, where we are right now in this moment, is smaller than equilibrium, then we don't have enough product. And that means that we're going to shift to the right and we're going to be making more product. Now let's say we have the same equation or same reaction, but this time, what numbers did I go with? Oh, I went with, let's say that A, let's rewrite this real quick. Our concentration of A is 2 molar, and our concentration of B is 10 molar. Okay, so already we can see that we have a higher concentration of product than we do of reactant, but we don't know if we're at equilibrium or not, because remember, these guys don't have to be equal. They just have to be constant. So let's take a look at that. So for our Q, we're going to put 10 over 2, which equals 5. So now our Q is greater than our K. So the equilibrium, or the constant that we're at right now, is higher than our equilibrium constant. And so that means we're going to shift back towards reactants. We're going to break down some of those products and go back to reserving reactants. Okay, so one more. We've got A going to B, but this time we've got 8 molar of our reactants, and we've got 16 molar of our products. Notice they are not equal, okay? But if we put our products divided by reactants, we get 2. And now, oh, and this is Q. And so now our Q is indeed equal to our K. So we are at equilibrium. So this means the rate of forward and reverse reactions is equal and constant. Our concentrations of our reactants and our products are constant, but as we can see here, not equal. And so now we can tell our system's at equilibrium. So that's how Q and K is used. So here we go. We are, let's take a look at using this in a problem. So here we have a reaction. We've got our equilibrium constant. Remember that for K and Kc, we only use gases and aqueous states of matter, and for Kp, we only use gas. No solids and liquids in these guys. So we really want to watch those states of matter. So just putting that back in there. We hadn't talked about that since the last episode, so I wanted to make sure we were remembering that. So we've got all of these guys here. We've got our equilibrium constant and a temperature, because remember, temperature can change our rate of reaction. In an experiment, we've got some concentrations here. Tried to keep it easy. Which direction will the reaction proceed to reach equilibrium? All right, let's set this up. I need a blank slide. Hold on one moment. All right, so I have my blank slide in place now. So first off, notice that nowhere in this problem does it say that we are at equilibrium. So if it doesn't say at equilibrium, then all these concentrations means that we are at initial concentrations. And remember, initial doesn't mean that the reaction hasn't been going on. It means at this point in time. That we're looking at this moment as time 0. There was stuff going on before then, but we're looking at it right now. So these concentrations are going to be our Q, because they are not at equilibrium. All right, so let's write this guy out. All right, so we have Q. Now I need to change to a darker color. Going back and forth here. All right, so we've got Q, and we're going to put our product on top, and we are going to write our expression first. So remember that expression does not have the numbers in it. We don't put the numbers in. We're just writing the relationship here. So what do we have there? What is our, oh, is it NOCl? Do we have an exponent there? We do. We got a little 2 there. So remember, those are those coefficients being brought in as exponents. Okay, so there we go. There we have our equilibrium, our reaction quotient, because we're talking about Q, our reaction quotient expression. So no numbers. All right, so now we got to bring the numbers in. They did not give us these numbers in concentration. They gave us moles and they told us in how many liters, so we got to do a little extra work, right? Okay, so let's put that in here. And yes, this is very easy math that you could just do in your head, but remember, we want to write everything out on a test or in research. Oh, and you know what? It's not in 1 liter. It is in 2 liters. That's an easy fix. So yeah, we could just do the calculations and throw down a number, but when we are taking an exam or when we are in research and we're keeping a lab notebook that we might use for a peer-reviewed article, we always want to use our calculations. It shows our work. It also is great that if research doesn't work out, you can go back and look and figure out where the mistake was. Even NASA scientists make mistakes in their calculations, right? Hence the Challenger blowing up because someone used the wrong units of measure. All right, so when we do these calculations, throw it into our calculator, we end up with 5 times 10 to the negative 9. All right, but as we saw, they gave us K, and the K was 1.55. I have to keep looking at my notes because I don't remember the numbers. 10 to the negative 5, and I don't want to flip back on the screen, give you motion sickness there going back and forth between slides. So our Q, hopefully, obviously, is smaller than our K. Excuse me. So if our initial, where we are right now in time, is smaller than K, we need to keep moving forward, right? And make some more product. There's not enough product, so we're going to keep moving forward. If Q were bigger than K, we would have made enough product and we could go back. All right. Sound good? Cool. Okay, well, let's take a look here. Solving equilibrium problems, we're always going to balance that equation, right? That's always number 1 in all chemistry. We write the equation and we balance it. We're going to write the equilibrium expression that is without numbers. We're going to list our initial concentrations. We're going to calculate our Q and determine the shift in equilibrium. Then we're going to define our concentrations at equilibrium. We're going to substitute those concentrations into the expression and solve. So there is a crazy way of doing this. It's called the ICE method. And we're going to take a look at that now. The best way to learn about this is to do it. It's just one of those things. And if you say to anyone who has gone through AP chemistry or college level chemistry, and you say, I learned about ICE problems or ICE table problems, they will know what you're talking about. There are different ways to do these kind of problems, but I will say that College Board and most college professors will want to see you do the problems in this format. So let's go ahead and take a look at a problem. Okay, so here is our reaction. Pretty easy. We're going to make sure it's balanced. we're going to make sure we look at our states of matter. We have gases throughout, so we're going to include all of that. And let's take a look. In a certain experiment, we have 2 moles of SO2, 1.5 moles of O2, and 3 moles of SO3. And they're placed in a 1-liter flask at equilibrium. 3.5 moles of SO3 were found to be present. Calculate the equilibrium concentrations of O2, SO2, and calculate the equilibrium constant. Okay, so grammar, like what is actually being said here, is as important as the numbers themselves. So notice here, oh, I want to change my color again. Okay, so notice here we have the word at equilibrium. Okay, so they're telling us that when we hit equilibrium, that's the we have 3.5 moles of SO3. So that means that all of this information is the concentrations at initial, oops, sorry about that, at initial or Q. Okay, so all these numbers are going to help us calculate Q. This number is going to help us calculate K. Well, for K, you need the concentration of products and reactants, so you need the concentrations of these guys too. So we need to figure a lot of stuff out, and that's where these ICE tables come in. So let's get a clean page here. I'm going to go up and grab a new color, as I'm writing on a white screen now. And along the side, we are going to write ICE, hence ICE, okay? And across the top, we are going to write our reaction. I have to keep looking at my notes because I don't remember what was on that screen before. Don't want to give you a whiplash going back and forth. And that is producing this guy. So we write that at the top. We're making a table. Okay, so we are going to actually solve this problem, but I want to put some notes in here. So I am going to grab a different color here to write my notes in. So I stands for, let's see how small I can, oh, I'll write it underneath. I stands for initial. Okay, so I is going to help us solve Q. E stands for, you got it, equilibrium. And I am not writing that whole word out. Okay, and so E is going to help us solve for K. Well, what's the C here, right? What's the deal there? So C stands for change. So in this row, we're going to write how things are changing to get us from the initial concentrations to the concentrations at equilibrium. All right. Was there anything else I wanted to say about that? Okay, so let's put some information in before we say more here. So what do we got? So they told us that we have 2 moles per 1 liter of this guy, which means we have 2 molar. And they told us that we have 1.5 moles of this guy per 1 liter. So that means we have 1.5 molar. And they told us at initial concentration, or where we are in our experiment at this time, we have 3 0.0 moles per 1 liter of this guy, which is 3 molar. Whew. That was some hard math right there, right? Okay. So they tell us this just in that problem that we had on the last slide there. Okay, so that's information given. So looking at this, we can solve for Q with that guy, right? We can pop these in there and solve for Q. So we need to figure out K to realize what our shift is, right? Okay, so let's go back to that prior slide. And they tell us at equilibrium, we have 3.5 moles of SO3. So I told you, you got to be really good at reading these problems. Like, it's not just about the numbers, it's about actually reading. So right there, we know oh, my little pad here is fighting me. So they're telling us that our initial concentration of SO3 is 3 molar, right? And they're telling us that at equilibrium, our SO3 is, what did they say? 3.5. So that means that we have had an increase in product, right? And so that means that our arrow is definitely going to be going in that direction. Oh, I'm sorry, I meant to write that up here. Wait, let's get rid of that guy. So that means that we are going in this direction at this point in time because we are making product. We end up with more product. So that means that our change, right, is going to be negative here, minus, we're going to lose some of that ingredient. We're going to lose some of that ingredient, and we are going to gain some of this ingredient, right? Because we are going from less to more of our product. So we're going to gain there. And law of conservation of mass, if we're making more here, we got to lose it here, right? But by how much are we going to gain and lose? Okay, so we know that it is going to be by X amount. But there's a relationship here of a ratio of how much is lost here compared to how much is lost here compared to how much is gained here. And where we get that number, I'm going to switch colors here. Where we get that number is from our coefficients. So we're going to pull down our coefficients here. And that is the ratio, right? Coefficients are a ratio. So for here, we're going to lose negative 2x because the ratio of this ingredient or reactant to this one is a 2 to 1. So this is going to be, we're going to lose 1x, and here we are going to gain 2x. So for every 2 we lose of SO2, we're going to lose 1 oxygen, and we're going to gain 2 SO3s. We just don't know what X is yet, but we know what that ratio is because that ratio comes from our coefficients. All right, so there we go. Now we can start figuring out our equilibrium, right? So we're going to take our initial concentration of 2, and we know we're going to lose 2x. So we're making an equation. We're bringing these things together. Here we have 1.5, and we're going to lose 1x. And here we have 3, and we are going to gain 2x. Okay, All right, so now we know at equilibrium, these are going to be our concentrations. Well, we need to solve for X so that we can solve this problem. Well, remember that we have the concentration of SO3 at equilibrium. So this problem right here is 3 plus 2x, I'm sorry, not problem, equation, is going to equal 3.5. So now we can solve for x. We do not need a calculator for this guy. And that is going to be 0.25. So now we can pop 0.25 back into all of these guys, right? So we're going to have 2 minus 2 times 0.25. Now, do you need to write all this out? No, I'm doing it so that everybody sees what's going on here. Right? And so we have the concentration there. So that means that our concentration of SO2 at equilibrium is going to be 1.50 molar. And our concentration of oxygen is going to be 1.25 molar. And then this guy, we already know our concentration here is 3.5, right? Okay, excellent. So now we can solve for K. So K, we are going to put 3.5. Got to have our coefficient there as the exponent. That's a 1.5. Coefficient is the exponent. This guy, no exponent because his coefficient is 1. And there we go. So we can solve for K, and that is going to be 4.36. No units. All right. And we can figure out Q, kind of running out of room here. We can figure out Q by putting these numbers in, right? I'm going to write this pretty quickly here. So we've got 3, 2, we've got 2. So I'm looking at these initial numbers to figure out my Q. 2, what do we got there? 1.5. Right? And so we can figure out Q and then see where we are in our reaction. Now, I believe the question, here I'm going to grab my highlighter. I believe the question asked for this number, and this number, just to answer the question. But we can solve for Q and figure out what our relationship is. Now, without even solving for it, we know that Q is going to be smaller than our K because we were heading toward product at our initial concentrations. So there we go. We solved a lot, didn't we? Pretty cool, right? All right. So let's look at another problem. All right, so we got the same reaction. You're going to use the same equation, but you've got different concentrations. You've got 0.5 moles, 0.35 moles. They're placed in a 1 liter container. When the system reaches equilibrium, 0.045 moles of O2 are present. What are the final concentrations of these guys and K? So right off the bat, what are you noticing that is different about this situation, aside the temperature, from the prior one? I'll give you a hint, and I'll give you the answer. In the initial concentrations, we have 0 oxygen. There is no oxygen present in our initial concentration. So go ahead and give this guy a try. Pause. I want you to try to do this one, set it up with ice, go back a slide if you need to, and then come back and I'm going to have the answer and talk it through with you. Okay, so here we are taking a look at the problem. So I rewrote that equation up at the top, and I got my ice here, put in the initial concentrations, and we were given the concentration of oxygen at equilibrium. So these are the things just given to us in the problem. So the first thing that I look at is that the concentration of oxygen is going from 0 at the initial time to 0.045. So that means that we are going towards reactants, right? Because we have 0 and we're gaining a reactant. So that means that our Q, oh, got to get in my pencil there. That means that our Q is going to be greater than K, right? Because we're going to be going back toward reactants. All right, shifting left. Okay, so that means that we are going to be adding to our reactants and subtracting from our products. It's still the same 2x, 1x, 2x, because that's our ratio, 2 to 1 to 2. And so let's make our formulas down here. Here we've got 0.5 plus 2x. Here we've got 0 plus 1x gives us 0.045. So hopefully we see pretty easily that that means that x equals 0.045. And here we have 0.35 minus 2x. All right, so we're going to pop x into these two guys, and we end up with a concentration here of 0.59 molar. And we end up with a constant that this is our concentration, right, of oxygen. And here we end up with a concentration of 0.26 molar. Okay, so there we go. So it was asking for us to figure out a concentration here and a concentration here. We also need to calculate for K. So we have K. We're going to put 0.26. We got to have that coefficient become our exponent. And then down below, we've got our product, 0.59. And we've got our coefficient as an exponent, and 0.045. Okay? And when we calculate that out, our K is 4.32. So our equilibrium constant is 4.32. And if we were to calculate out Q, which we could right here, we would see that it would be greater than 4.32 because it is moving toward the left. All right. Good job, guys. Okay, let's take a look at another problem. Okay, this is a type 2 problem, which means we're given starting concentrations and K. So carbon dioxide reacts with the system to produce, carbon monoxide reacts with the system to produce carbon dioxide and hydrogen gas. At 700 Kelvin, the equilibrium constant is 5.10. Calculate the equilibrium concentrations of all the species if 1 mole of each component is mixed in a 1 liter flask. All right, pause and give that a go. If anything, just set up your ice table and what you have known there, what knowns they're giving you in the problem, and then come back and take a look at the answer. Okay, so here you can see I've set up the problem with my knowns. I've written my chemical equation, including states of matter. States of matter are important here. And I've made sure I have a balanced equation. Written out ice, got the initial concentrations, which in the problem they've written is 1 mole of each component in a 1 liter flask. So 1/1 gives us 1 molar for everything. We were not given anything at equilibrium, but we were given the equilibrium constant. Okay, so if we have all of these guys, then we can figure out Q, right? So the first thing that we're going to figure out is Q. And we've got 1 times 1 divided by 1 times 1, so obviously Q is 1. So when we bring these guys together, we see that Q is greater than K, and that means that we are going to have a, I'm sorry, no, Q is not greater than K. I was just checking, making sure you're paying attention there. 1 is not greater than 5. Q is less than K. And so we're going to have a shift to the right. We're going to need to make more product. So that means that our reactants are going to reduce and our products are going to increase. We see our ratio is 1. Couldn't ask for easier numbers, right? So these are all 1x. And so therefore, at equilibrium, we're going to have 1 minus 1x, 1 minus 1x, 1 plus 1x, 1 plus 1x. Oh, that's not really an x. Okay. All right. So now we need to put this all together. So our K, which equals 5.1, is going to be equal to the concentration of carbon dioxide times the concentration of H2 divided by concentration of carbon monoxide times the concentration of water. And we can include all of them because they are all gases. And so now we're going to fill this all this stuff in. So we've got 1 plus 1x, 1 plus 1x divided by 1 minus 1x, 1 minus 1x. Alrighty. And when we pop that into our calculator, we get that x, we're going to solve for x. X is going to equal 0.386. All right, so that means x equals 0.386. Remember, they're looking for concentrations, so our concentrations of our products, we've got to add, so that's going to equal 1.386, and the concentration of our reactants equals 1 minus 0.386. And so we get 0.613 molar. All right, and just to confirm, what was it asking for? Calculate the equilibrium concentrations for all the species. So this is our final answer. And you would want to write these out, like actual concentration of carbon dioxide, and so forth, not abbreviate it like I did there. All right, that is an awesome job for today. Join me next time on doing more ice problems. All right, see you guys later. Bye.